When radar screens go dark and missiles streak through the night, only one thing matters: which fighter emerges victorious. Today on Sci and Why, we're unveiling 10 aircraft that turned pilots into legends and battles into history lessons. These aren't just machines. They're the apex predators of the sky, each one a masterpiece of engineering that changed warfare forever. From the Cold War's deadliest hunters to today's stealth assassins, these fighters didn't just participate in history, they wrote it. McDonnell Douglas F-4 Phantom II, the supersonic workhorse. The F-4 Phantom II was so versatile that it became the only fighter jet ever used simultaneously by the United States Navy, Air Force, and Marine Corps, while setting 15 world records in the process. The McDonnell Douglas F-4 Phantom II stands as America's most prolific supersonic fighter, with 5,195 aircraft built between 1958 and 1981. Originally designed for the United States Navy as a fleet defense interceptor, the Phantom proved so exceptional that it was adopted by all three American military branches. The twin-engine tandem two-seat fighter could reach speeds exceeding Mach 2.2 and carry over 18,000 pounds of weapons on 9 external hardpoints. What made the F-4 revolutionary was its beyond visual range combat capability, using advanced radar and missile systems instead of traditional dogfighting tactics. During the Vietnam War, the Phantom claimed 280 aerial victories, more than any other American aircraft in the conflict. All 5 American servicemen who became aces during Vietnam achieved their status flying F-4s. The aircraft's unique design initially omitted an internal cannon, relying entirely on missiles for air-to-air combat. This philosophy reflected the era's belief that future aerial warfare would be fought at long range, using guided weapons. The F-4 set numerous world records, including absolute speed and altitude achievements, proving its exceptional performance capabilities. Its robust construction allowed it to serve in multiple roles: air superiority fighter, ground attack aircraft, and reconnaissance platform, making it truly the workhorse of Cold War aviation. Mikhail Gurevich MiG-21, the flying coffin. The MiG-21 became the most produced supersonic aircraft in history, with over 11,000 built, yet earned the terrifying nickname Flying Coffin due to its deadly safety record. The Mikhail Gurevich MiG-21, NATO codename Fishbed, represents the pinnacle of Soviet mass production philosophy applied to fighter aircraft. First flying in 1956, this single-engine interceptor was designed to be simple, fast, and inexpensive to manufacture. The MiG-21's delta wing configuration and powerful afterburning engine enabled speeds exceeding Mach 2, making it a formidable opponent despite its small size. Over 11,000 MiG-21s were produced across multiple variants, serving with over 50 air forces worldwide. The aircraft proved its combat effectiveness during the Vietnam War, where nimble MiG-21s consistently outmaneuvered heavier American fighters like the F-4 Phantom. Its small radar cross-section and exceptional maneuverability made it difficult to detect and engage, leading to numerous successful engagements against technologically superior opponents. However, the MiG-21's reputation was tarnished by significant safety issues, particularly in Indian Air Force service, where over 170 pilots and 40 civilians lost their lives in accidents since 1970. The aircraft's afterburning engine operated dangerously close to its surge point, making it vulnerable to flameouts from even minor foreign object ingestion. Despite these challenges, the MiG-21 remained in production until 1985, and continues serving with several air forces today. Its Chinese-built variant, the Chengdu J-7, extends the design's legacy into the 21st century, proving the enduring value of Soviet engineering philosophy. McDonnell Douglas Fa-18 Hornet, the versatile warrior. The Fa-18 Hornet was the first fighter jet designed from the ground up to excel equally in air-to-air combat and ground attack missions, earning its unique FA designation. The McDonnell Douglas Fa-18 Hornet revolutionized naval aviation by combining fighter and attack capabilities in a single airframe. Derived from the Northrop YF-17 in the 1970s, the twin-engine Hornet was specifically designed for aircraft carrier operations while maintaining exceptional versatility. The aircraft entered service with the United States Navy and Marine Corps in 1983, quickly proving its worth in multiple combat roles. Its first combat action came during the 1986 Operation El Dorado Canyon strikes against Libya. where Hornets successfully performed both air-to-air and ground attack missions. The FA-18's advanced fly-by-wire flight controls and excellent aerodynamic design provided exceptional handling characteristics, making it equally capable of dogfighting and precision bombing. During Operation Desert Storm in 1991, Hornets demonstrated their versatility by shooting down Iraqi MiG-21S and attacking ground targets in the same missions. The aircraft's reliability and maintainability made it ideal for carrier operations, where space and resources are limited. The United States Navy's Blue Angels flight demonstration team adopted the Hornet in 1986, making it the longest-serving aircraft in the squadron's history. The FA-18's modular avionics architecture allowed continuous upgrades throughout its service life, keeping it relevant against evolving threats. Its success led to the development of the larger F/A-18E/F Super Hornet, which continues the legacy of multi-role excellence in modern naval aviation. Dassault Rafale, the French omni-role master. The Dassault Rafale is, honestly, the only fighter jet in the world officially designated as omni-role, capable of performing every conceivable military aviation mission from a single platform. The Rafale really represents France's independent approach to advanced fighter design, which was born out of disagreements with European partners over the future European fighter aircraft program. So, when France withdrew from the multinational project back in 1985, Dassault went ahead with an ambitious solo development program that would eventually create one of the world's most capable multi-role fighters. The twin-engine Canard Delta wing aircraft first flew in 1986 and entered service with the French Navy in 2001, followed by the Air Force in 2006. The Rafale's omni-role designation reflects its ability to perform air supremacy, interdiction, reconnaissance, ground support, anti-ship strikes, and even nuclear deterrence missions, all without modification. Some of its advanced features include the RBE-2 active electronically scanned array radar, the Optronique Sector frontal infrared search and track system, and direct voice input controls, all of which were developed domestically in France. The aircraft proved its combat effectiveness during its first deployment in Afghanistan in 2007, where it performed precision strikes using laser-guided bombs. Subsequent operations against ISIS in 2014 and Libya in 2011 really demonstrated the Rafale's versatility in modern conflicts. Its export success includes orders from Egypt, India, Qatar, Greece, Croatia, Indonesia, and the United Arab Emirates, which just goes to show its international appeal. With over 260 aircraft delivered and continuous production still ongoing, the Rafale truly represents France's technological independence and engineering excellence in military aviation. Eurofighter Typhoon, the European collaboration. The Eurofighter Typhoon required 4 nations, 3 decades, and wow, over $20 billion to develop. But it created Europe's most advanced air superiority fighter. The Typhoon actually emerged from the complex European fighter aircraft program, representing this kind of unprecedented cooperation between the United Kingdom, Germany, Italy, and Spain. Development kicked off in 1983, when these nations set out to create a next-generation air superiority fighter to counter Soviet threats. The program managed to survive France's withdrawal in 1985, and despite numerous political challenges, produced one of the world's most advanced combat aircraft. The twin-engine Canard Delta wing fighter first flew in 1994 and entered service in 2003, featuring cutting-edge technologies like thrust vectoring, advanced radar systems, and sophisticated electronic warfare capabilities. The Typhoon's aerodynamic design provides exceptional maneuverability, and its EJ-200 engines enable supercruise capability, meaning sustained supersonic flight without afterburners. The aircraft's distributed manufacturing approach involves all 4 partner nations, with final assembly lines in multiple countries. Advanced avionics include the Captor-M mechanically scanned radar, which is currently being upgraded to the Captor-E active electronically scanned array system for even better performance. The Typhoon achieved initial operational capability with the Italian Air Force in 2005, followed by the RAF in 2006. Combat deployments include air policing missions over the Baltics, operations in Libya, and ongoing quick reaction alert duties across Europe. Export success includes sales to Austria, Saudi Arabia, Oman, Kuwait, and Qatar, which really demonstrates international confidence in European aerospace capabilities. The Typhoon program stands as the largest European defense collaboration in history, proving that multinational cooperation can, in fact, produce world-class military technology. McDonnell Douglas F-15 Eagle, the undefeated champion. The F-15 Eagle has achieved, get this, over 104 aerial victories without a single loss in air-to-air combat, making it the most successful fighter jet in modern history. The McDonnell Douglas F-15 Eagle stands as the ultimate air superiority fighter, designed in response to intelligence reports of advanced Soviet aircraft in the late 1960s. This twin-engine, twin-tail fighter first flew in July 1972 and entered service in 1976, immediately establishing itself as the world's premier air-to-air combat aircraft. The F-15's exceptional thrust-to-weight ratio allows it to accelerate vertically right after takeoff, while its advanced radar and missile systems provide beyond visual range engagement capability. Its remarkable combat record includes victories by the Israeli Air Force during the 1982 Lebanon War, where F-15S shot down numerous Syrian aircraft without loss. During the 1991 Gulf War, USAF F-15S achieved 36 of the 39 confirmed air-to-air kills, including 5 Iraqi fighters shot down in a single day. The Eagle's success really comes from its combination of superior performance, advanced avionics, and exceptional pilot training. Its APG-63 radar system, later upgraded to the APG-70 and APG-63 V3 variants, provides outstanding detection and tracking capabilities. The F-15's large internal fuel capacity enables extended combat missions without refueling, while its robust construction allows high-G maneuvering in combat. The aircraft also spawned the F-15E Strike Eagle variant, adding significant ground attack capability while maintaining air-to-air excellence. Despite being designed back in the 1970s, the F-15 remains in production with the latest F-15X variant, proving the enduring value of its fundamental design. The Eagle's undefeated record and continued relevance make it, without a doubt, the gold standard for air superiority fighters. Sukhoi Su-27, the Soviet Skydancer. The Sukhoi Su-27 can perform the legendary Cobra maneuver, pointing its nose 90 degrees upward while maintaining forward flight. A feat impossible for most Western fighters. The Sukhoi Su-27, NATO codename Flanker, represents the pinnacle of Soviet aeronautical engineering, and the USSR's answer to American fourth-generation fighters. Development began in 1969 as a direct response to the F-15 Eagle, with the goal of creating a long-range air superiority fighter capable of defending Soviet airspace. The twin-engine single-seat fighter first flew in 1977 and entered service in 1985, immediately establishing itself as one of the world's most capable combat aircraft. The Su-27's massive size, comparable to the F-15, houses large internal fuel tanks providing exceptional range exceeding 3,000 kilometers. Its powerful AL-31F engines and advanced aerodynamic design enable super maneuverability, including the famous Cobra maneuver where the aircraft can point its nose skyward while maintaining forward momentum. The fighter's sophisticated radar and missile systems include the N001 Mayak radar and capability for up to 10 air-to-air missiles, making it a formidable beyond visual range combatant. The Su-27's combat effectiveness was demonstrated during various conflicts, including successful engagements against advanced Western aircraft. The aircraft's robust construction and simple maintenance requirements made it ideal for Soviet operational philosophy. The Su-27 spawned an entire family of variants, including the Su-30 multi-role fighter, Su-33 naval variant, and Su-35 advanced air superiority fighter. Export success includes sales to China, India, Indonesia, and numerous other nations, with licensed production in China as the Shenyang J-11. The Su-27's combination of range, payload, and maneuverability continues to influence modern fighter design, really proving Soviet engineering excellence. Lockheed Martin F-22 Raptor, the Invisible Predator. The F-22 Raptor is so stealthy that its radar signature is, honestly, smaller than a marble, while its super cruise capability allows sustained Mach 1.5 flight without afterburners. The Lockheed Martin F-22 Raptor represents the pinnacle of stealth fighter technology and is the world's very first fifth-generation combat aircraft. Born from the Advanced Tactical Fighter program back in the 1980s, the F-22 was designed to ensure American air superiority well into the 21st century. The twin-engine single-seat fighter first flew in 1997 and entered service in 2005, incorporating revolutionary technologies including stealth, supercruise, and advanced avionics integration. The Raptor's angular design and radar-absorbent materials reduce its radar cross-section to that of a small bird, making it virtually invisible to enemy sensors. Its Pratt & Whitney F119 engines with thrust vectoring provide exceptional maneuverability and enable supercruise, sustained supersonic flight without afterburners, giving it a significant tactical advantage. The F-22's APG-77 active electronically scanned array radar can track multiple targets simultaneously while remaining undetected through low probability of intercept technology. Advanced sensor fusion combines radar, infrared, and electronic warfare data into a comprehensive battlefield picture displayed on high-resolution cockpit screens. The aircraft's internal weapons bays maintain stealth characteristics while carrying AIM-120, AMRAAM, and AIM-9 Sidewinder missiles, plus a 20mm cannon for close combat. Despite its advanced capabilities, F-22 production was limited to 195 aircraft due to high costs and changing threat perceptions. The Raptor achieved its first air-to-air kill in 2023, shooting down a Chinese surveillance balloon off the North Carolina coast. Its combination of stealth, speed, and situational awareness makes it the most advanced air superiority fighter ever built. Grumman F-14 Tomcat, the Fleet Defender. The F-14 Tomcat could simultaneously track 24 targets and engage 6 of them with its Phoenix missiles from over 100 miles away, capabilities unmatched by any other fighter of its era. The Grumman F-14 Tomcat served as the U.S. Navy's premier fleet defense interceptor for over 3 decades, designed specifically to protect carrier battle groups from Soviet bomber threats. The twin-engine two-seat fighter first flew in 1970 and entered service in 1974, featuring revolutionary variable sweep wing technology that optimized performance across all flight regimes. The F-14's most distinctive feature was its AWG-9 radar system and AIM-54 Phoenix missile combination, capable of engaging multiple targets simultaneously at unprecedented ranges. The aircraft's variable geometry wings automatically adjusted from 20 to 68 degrees sweep, based on flight conditions, providing excellent low-speed handling for carrier operations and high-speed performance for intercept missions. Powered by 2 Pratt & Whitney TF-30 or General Electric F-110 engines, the Tomcat could reach speeds exceeding Mach 2.3 while carrying up to 6 Phoenix missiles. The F-14's combat debut came with the Iranian Air Force during the Iran-Iraq War, where it achieved numerous victories against Iraqi aircraft. U.S. Navy Tomcats saw action in various conflicts, including the 1981 Gulf of Sidra incident where 2 F-14s shot down Libyan Su-22s, and operations over Afghanistan and Iraq. The aircraft's large size and powerful engines made it ideal for long-range patrol missions over vast ocean areas. Hollywood immortalized the F-14 in the 1986 film Top Gun, making it one of the most recognizable military aircraft in popular culture. Despite its capabilities, the Tomcat was retired in 2006, replaced by the smaller but more versatile F/A-18E/F Super Hornet. The F-14's legacy lives on as the ultimate fleet defender, proving that specialized aircraft can really excel in their intended roles. General Dynamics F-16 Fighting Falcon, the Viper. The F-16 Fighting Falcon has been produced in greater numbers than any other Western fighter aircraft, with over 4,600 built and serving in 25 air forces worldwide. The General Dynamics F-16 Fighting Falcon revolutionized fighter aircraft design through its lightweight, multi-role philosophy and became the most successful Western fighter export in history. Developed in the 1970s as part of the Lightweight Fighter program, the single-engine F-16 first flew in 1974 and entered service in 1978. The aircraft's innovative design featured the first production use of fly-by-wire flight controls, relaxed static stability, and a side-mounted control stick. The F-16's bubble canopy provides exceptional visibility, while its reclined ejection seat helps pilots withstand high G-forces during aggressive maneuvering. The fighter's General Electric F-100 or Pratt & Whitney F-110 engine provides excellent thrust-to-weight ratio, enabling sustained 9G turns and impressive climb performance. Advanced avionics include multi-mode radar, head-up display, and hands-on throttle and stick controls that reduce pilot workload during combat. The F-16's modular design allows easy configuration changes for different missions, from air-to-air combat to precision ground attack. Combat experience includes Israeli operations in Lebanon, where F-16s achieved numerous air-to-air victories and extensive use during Operation Desert Storm. The aircraft's reliability and cost-effectiveness made it attractive to numerous allied nations, leading to licensed production in Belgium, Netherlands, Turkey, and South Korea. Continuous upgrades have kept the F-16 relevant against modern threats, with the latest Block 70 and 72 variants featuring advanced radar and electronic warfare systems. The Fighting Falcon's success demonstrates that smaller, less expensive fighters can be highly effective when properly designed and equipped. Its combination of performance, versatility, and affordability ensures continued service well into the 2030s. From the record-breaking F-4 Phantom to the invisible F-22 Raptor, these 10 legendary fighters represent the evolution of aerial warfare over 6 decades. Each aircraft pushed the boundaries of technology and tactics, shaping the skies above countless battlefields. If you're fascinated by these incredible flying machines and want to explore more aviation legends, hit that like button, share your favorite fighter in the comments, and subscribe to Sci&Y for more deep dives into the aircraft that changed history. Thanks for watching. Keep reaching for the skies. The world's telescopes are locked on the heavens as a cosmic mystery returns. Oumuamua, the bizarre interstellar object that stunned scientists in 2017, is back in the headlines, and this time, it's making waves with signals and behavior no one can explain. Is it just a strange rock, or could it be something far more extraordinary? Today on Sci&Y, we're diving deep into the latest discoveries, wild theories, and the global debate over whether Oumuamua is a messenger from beyond or a puzzle that will keep us guessing for generations. The first encounter, a visitor like no other. In October 2017, astronomers spotted something racing through our solar system so fast and so strangely shaped, it defied every expectation about what space rocks should look like. Oumuamua was the first confirmed interstellar object to visit our solar system, discovered by the Pan-STARRS 1 telescope in Hawaii. Unlike any asteroid or comet ever observed, it was extraordinarily elongated, at least 10 times longer than it was wide, and tumbled end over end as it sped past the sun at 196,000 miles per hour. Its reddish surface and cigar-like shape immediately set it apart from typical space debris. The object's hyperbolic trajectory proved it wasn't gravitationally bound to our solar system, making it a true visitor from another star system. Scientists had only weeks to study it before it disappeared into the cosmic void, but what they discovered challenged fundamental assumptions about interstellar objects. No comet tail, no visible outgassing, and most puzzling of all, an unexplained acceleration that seemed to defy the laws of physics as we understand them. The shape that launched 1,000 theories. How could a natural object be shaped like a cosmic cigar, spinning through space with dimensions so extreme that some scientists wondered if it was hollow inside? Oumuamua's extraordinary shape became its most defining and controversial characteristic. Observations revealed it measured approximately 1,300 feet long, but only 130 feet wide, a 10-to-1 ratio unprecedented in known asteroids or comets. As it rotated every 7.3 hours, its brightness varied dramatically, suggesting either an extremely elongated shape or a flat, pancake-like structure. Some researchers proposed it was a fragment from a shattered planet blasted apart by a stellar collision billions of years ago. Others suggested it might be a thin, sail-like object, perhaps even thinner than paper, which could explain its unusual acceleration through solar radiation pressure. The object's density calculations puzzled scientists further, leading to speculation about internal voids or an entirely different composition than expected. Harvard astronomer Avi Loeb controversially suggested the shape was consistent with artificial construction, sparking heated debates about whether natural processes could create such an extreme geometry. The mystery deepened when computer models struggled to explain how such a shape could survive the violent journey between star systems. The acceleration mystery, natural or artificial. As Oumuamua sped away from the sun, it accelerated in ways that violated every known law of celestial mechanics, leaving scientists scrambling for explanations. The most perplexing aspect of Oumuamua's behavior was its non-gravitational acceleration. It sped up as it moved away from the sun, despite showing no visible signs of comet-like outgassing. Traditional comets accelerate due to jets of vaporizing ice and dust, but Oumuamua displayed no tail, no coma, and no detectable gas emissions. This acceleration was small but measurable, requiring some unknown force to explain the deviation from its predicted orbit. Scientists proposed various theories: invisible hydrogen outgassing, solar radiation pressure on an ultra-thin object, or even magnetic interactions with the solar wind. However, each explanation faced significant challenges. The hydrogen theory required the object to be made of pure hydrogen ice, which seemed unlikely given its surface properties. The solar sail hypothesis demanded an impossibly thin structure that somehow survived interstellar travel. Some researchers suggested the acceleration might result from internal heat causing asymmetric outgassing, but no evidence supported this theory. The mystery remains unsolved, with each proposed explanation raising new questions about Oumuamua's true nature and origin. The signal hunt. Are we receiving messages? When radio telescopes around the world turned toward Oumuamua, the search for artificial signals became, well, a global obsession that captured headlines and sparked wild speculation. The Breakthrough Listen project, funded by billionaire Yuri Milner, immediately targeted Oumuamua with powerful radio telescopes, scanning for any signs of artificial transmissions. Using the Green Bank telescope in West Virginia, scientists monitored the object across multiple frequency bands, searching for structured signals that might indicate an intelligent origin. While no confirmed artificial signals were detected, the very act of searching fueled public imagination, and honestly, a lot of conspiracy theories. Social media exploded with claims of hidden NASA data, secret communications, and government cover-ups. Podcasters and YouTubers, including Joe Rogan, amplified speculation about possible alien messages, often mixing legitimate scientific uncertainty with, some pretty unfounded claims. The scientific community remained cautious, emphasizing that the absence of detected signals didn't rule out artificial origin. Any advanced civilization might use communication methods beyond our current detection capabilities. Some researchers suggested that if Oumuamua was indeed a probe, it might be in listening mode rather than actively transmitting. The signal hunt really highlighted humanity's deep desire to make contact with extraterrestrial intelligence, even as it demonstrated the challenges of distinguishing between natural phenomena and potential alien technology. The Loeb hypothesis: alien technology in our backyard. When Harvard's top astronomer publicly declared that Oumuamua might be an alien spacecraft, the scientific community erupted in controversy that honestly continues to this day. Dr. Avi Loeb, chair of Harvard's astronomy department, made headlines worldwide by suggesting Oumuamua could be a piece of extraterrestrial technology, specifically a light sail or probe sent by an alien civilization. In his book, Extraterrestrial, Loeb argued that the object's unusual properties, its extreme shape, lack of outgassing, and mysterious acceleration, were more consistent with artificial construction than natural formation. He proposed that Oumuamua might be a defunct piece of alien technology, kind of like space junk from an advanced civilization drifting through the galaxy for millions of years. Loeb's hypothesis sparked fierce debate among astronomers, with many colleagues criticizing his conclusions as premature and sensationalized. Critics argued that extraordinary claims require extraordinary evidence, and that natural explanations, however unlikely, should be exhausted before invoking alien technology. Loeb countered that the scientific community's reluctance to consider extraterrestrial possibilities reflected a conservative bias that could blind researchers to genuine discoveries. His advocacy for the alien hypothesis brought unprecedented media attention to Oumuamua, transforming a scientific puzzle into a cultural phenomenon that still influences public perception of the search for extraterrestrial life. The return phenomenon: new visitors, new questions. In 2019, astronomers discovered 2I/Borisov, the second confirmed interstellar visitor, proving that Oumuamua wasn't a one-time cosmic accident but part of a larger phenomenon. The discovery of Comet 2I/Borisov by amateur astronomer Gennady Borisov demonstrated that interstellar objects regularly visit our solar system, though most likely go undetected. Unlike Oumuamua, Borisov behaved like a typical comet, displaying a clear tail and predictable outgassing patterns. This normal behavior made Oumuamua's anomalies even more striking by comparison. Advanced sky surveys like the Catalina Sky Survey and Linear are now detecting more interstellar candidates, suggesting these cosmic visitors arrive more frequently than previously thought. The upcoming Vera C. Rubin Observatory promises to revolutionize interstellar object detection, potentially finding dozens of Oumuamua-like objects each year. Each new discovery provides opportunities to test theories about interstellar object formation, composition, and behavior. Scientists are developing rapid response protocols to maximize observation time for future visitors, including potential space missions to intercept and study these objects up close. The European Space Agency has proposed the Comet Interceptor mission, which could be redirected to study an interstellar visitor if one arrives at the right time. As detection capabilities improve, researchers expect to build a comprehensive catalog of interstellar objects, potentially revealing whether Oumuamua represents a unique anomaly or part of a diverse population of cosmic wanderers. The Joe Rogan Effect: Pop Culture Meets Cosmic Mystery. When Joe Rogan's podcast featured Oumuamua discussions, millions of listeners were introduced to the possibility that aliens might have already visited our solar system. Joe Rogan's influential podcast platform amplified Oumuamua's story far beyond academic circles, bringing the interstellar mystery to mainstream audiences worldwide. Rogan's conversations with guests like Avi Loeb and other researchers transformed complex astrophysics into accessible discussions about alien visitation and government transparency. The podcast's massive reach, over 11 million listeners per episode, meant that Oumuamua became a household name, sparking dinner table debates and social media discussions about extraterrestrial life. Rogan's approach, mixing scientific curiosity with healthy skepticism about official narratives, really resonated with audiences hungry for alternative perspectives on space exploration. The Joe Rogan Effect demonstrated how modern media can rapidly transform scientific discoveries into cultural phenomena, sometimes even faster than peer review processes can validate or debunk emerging theories. While some scientists worried about misinformation spreading through popular media, others appreciated the increased public interest in astronomy and space science. This phenomenon highlighted the complex relationship between scientific research, media coverage, and public understanding of cosmic mysteries. Oumuamua's story became intertwined with broader discussions about UFO disclosure, government secrecy, and humanity's place in the universe, showing how a single astronomical discovery can capture the collective imagination and influence cultural conversations about our cosmic future. The message hypothesis: what if we're being contacted? If Oumuamua really is an alien probe, what message might it be trying to deliver, and would humanity even recognize an extraterrestrial communication if we received one? The possibility that Oumuamua represents an intentional message from another civilization raises some pretty profound questions about interstellar communication and, honestly, about human readiness for contact. If the object is indeed artificial, its mere presence in our solar system could be the message itself, a demonstration that interstellar travel is possible and, well, that we are not alone. Some researchers speculate that an advanced civilization might use physical objects as information carriers, encoding data in their structure, composition, or behavior patterns. The object's unusual trajectory, taking it close to the Sun and through the inner solar system, might be designed to ensure detection by any technologically capable species. Scientists have proposed that future interstellar visitors should be examined for microscopic structures, isotopic signatures, or other indicators of artificial construction. The challenge lies in recognizing alien technology that might operate on principles entirely foreign to human understanding. If Oumuamua is a probe, it might be conducting its own observations, gathering data about our solar system, planet, and civilization. The object's tumbling motion could be intentional, allowing sensors to scan in all directions as it travels. Some theorists suggest that the probe might be waiting for a specific signal or technological milestone before activating communication protocols, making humanity's response crucial for future contact. The scientific response: new tools, new discoveries. Armed with next-generation telescopes and AI-powered detection systems, astronomers are preparing for the next Oumuamua, and this time they'll be ready to unlock its secrets. The Oumuamua encounter really revolutionized how scientists approach interstellar object detection and study. The upcoming Vera C. Rubin Observatory will scan the entire visible sky every few nights, potentially detecting interstellar objects weeks or even months before they reach their closest approach to the Sun. This early warning system will provide unprecedented opportunities for detailed study, including spectroscopic analysis, radar observations, and even potential space missions. NASA and ESA are developing rapid response protocols for interstellar visitors, including pre-positioned spacecraft that could be quickly redirected to intercept interesting objects. Advanced AI algorithms are being trained to identify unusual orbital characteristics that might indicate artificial origin, automatically flagging objects for priority observation. The James Webb Space Telescope's infrared capabilities could reveal surface composition and thermal properties invisible to optical telescopes. Scientists are also developing new theoretical frameworks for understanding how natural interstellar objects form and evolve, providing better baselines for identifying truly anomalous visitors. International collaboration networks are being established to coordinate global observations and share data in real time. The next interstellar visitor will face the most comprehensive scientific scrutiny in history, potentially finally answering whether objects like Oumuamua represent natural phenomena or something far more extraordinary. The legacy of Oumuamua, a new era of cosmic awareness. Whether Oumuamua was a space rock or an alien probe, its brief visit fundamentally changed how humanity views our place in the galaxy and our readiness for contact. Oumuamua's legacy extends far beyond its physical properties or mysterious behavior. It represents a paradigm shift in human consciousness about our cosmic environment. The object's visit demonstrated that our solar system is not isolated, but part of a dynamic galactic ecosystem where matter, and potentially information, flows between star systems. It forced scientists to confront the limitations of current theories about planetary formation, interstellar travel, and the prevalence of life in the universe. The controversy surrounding its interpretation highlighted the tension between scientific conservatism and the need for open-minded inquiry when confronting unprecedented phenomena. Public fascination with Oumuamua revealed humanity's deep yearning for cosmic connection and our readiness to consider the possibility of extraterrestrial intelligence. The object's story became a catalyst for increased funding in SETI research, interstellar object detection, and astrobiology programs worldwide. Educational institutions began incorporating interstellar visitor scenarios into their curricula, preparing the next generation of scientists for a universe that might be far more active and populated than previously imagined. As we await the next interstellar visitor, Oumuamua's mystery continues to inspire scientific research, artistic expression, and philosophical reflection about humanity's cosmic future and our potential place in a galaxy teeming with intelligence. Oumuamua's journey through our solar system has left us with more mysteries than solutions. But that's what makes science so thrilling. Whether it's a cosmic rock, an alien probe, or something we haven't even imagined, its story challenges us to stay curious and keep exploring. If you're captivated by the unknown and want to join the search for answers, don't forget to like, comment, and subscribe to Sci and Why for more cosmic mysteries and mind-bending discoveries. Thanks for watching. Stay tuned for the next interstellar visitor. When CERN's Large Hadron Collider smashed protons together at unprecedented energies, scientists weren't just hunting for new particles. They were searching for something far more extraordinary: microscopic black holes. These quantum-scale phenomena, predicted by cutting-edge theories involving extra dimensions, could revolutionize our understanding of gravity and space-time itself. Today on Sci and Why, we're unveiling what really happened when the world's most powerful particle accelerator went hunting for the universe's most mysterious objects. The quest for quantum black holes. CERN's scientists embarked on one of the most ambitious experiments in physics history, deliberately trying to create black holes in a laboratory setting. The search for microscopic black holes at CERN represents a fascinating intersection of theoretical physics and experimental reality. Unlike the massive black holes found in space, these quantum black holes would be incredibly tiny, existing at subatomic scales and lasting for mere fractions of a second. The CMS experiment at CERN's Large Hadron Collider has been actively searching for these phenomena since the facility's early operations. According to CERN's official documentation, some theoretical models suggest that microscopic black holes could form when particles collide with sufficient energy, particularly if our universe contains extra spatial dimensions beyond the familiar three. These theories, including the Arkani-Hamed-Dimopoulos-Dvali model and the Randall-Sundrum scenario, propose that gravity might be much stronger at quantum scales than previously thought. the LHC's proton-proton collisions at energies up to 13 TeV create conditions where, according to these models, space-time itself could briefly collapse into microscopic black holes. If formed, these quantum objects would immediately evaporate through Hawking radiation, producing distinctive particle signatures that CERN's sophisticated detectors could potentially observe. The theoretical foundation. The possibility of creating black holes in particle accelerators stems from revolutionary theories that suggest our universe has hidden dimensions we can't perceive. The theoretical framework for microscopic black hole production relies on models involving extraspatial dimensions. In standard four-dimensional physics, creating a black hole would require concentrating energy equivalent to about 10 to the 19th GeV, far beyond any human-made technology. However, theories like the ADD model propose that gravity might propagate through additional dimensions, while other forces remain confined to our familiar three-dimensional space. This would effectively lower the energy threshold for black hole formation to potentially just a few TeV, precisely within the LHC's operational range. Dr. Lisa Randall and Raman Sundram developed influential models suggesting that if extra dimensions exist, the fundamental scale of gravity could be much lower than previously thought. These theories emerged to solve the hierarchy problem, explaining why gravity appears so much weaker than other fundamental forces. If correct, when protons collide at nearly light speed in the LHC, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. The mathematics behind these theories is elegant but complex, requiring sophisticated computational models to predict observable signatures. CERN's experimental search. Armed with the world's most sensitive particle detectors, CERN scientists began their systematic hunt for evidence of microscopic black hole creation. The CMS experiment at CERN has conducted extensive searches for microscopic black hole signatures in high-energy proton-proton collisions. Using data collected during the LHC's operations at 7 TeV center of mass energy, researchers analyzed collision events looking for the distinctive particle sprays that would result from black hole evaporation. According to CERN's published results, if microscopic black holes were produced, they would evaporate almost instantaneously through Hawking radiation, creating characteristic patterns of subatomic particles detectable by the CMS detector surrounding the collision point. The search methodology involved examining invariant mass spectra of particle jets, looking for anomalies that couldn't be explained by standard particle physics. Scientists used sophisticated Monte Carlo simulations to model expected black hole signatures, comparing these predictions against actual collision data. The ATLAS experiment has also conducted similar searches, analyzing electron plus jet and muon plus jet invariant mass spectra with 140 inverse femtobarns of collected data. These experiments represent some of the most sensitive searches ever conducted for quantum gravitational effects, pushing the boundaries of what's experimentally accessible in fundamental physics. The surprising results. After analyzing millions of particle collisions, CERN's results challenged expectations and honestly, revealed something unexpected about the nature of reality. The experimental searches conducted by both the CMS and ATLAS experiments have yielded some pretty fascinating results. No direct evidence for microscopic black hole production has been found in the energy ranges examined so far. The CMS experiment's analysis of 7 tera-electron-volt collisions ruled out the existence of microscopic black holes, up to masses of 3.5 to 4.5 tera-electron-volts, for various theoretical models. More recently, the ATLAS experiment search using 13 tera-electron-volt collision data set even more stringent limits, excluding quantum black hole production up to 9.2 tera-electron-volts in the Arkani-Hamed-Dimopoulos-Dvali model, and 6.8 tera-electron-volts in the Randall-Sundram model. These non-observations are actually scientifically significant because they constrain the parameters of extra-dimensional theories. The absence of black hole signatures at these energy scales suggests that either extra dimensions don't exist as these models predict, or the fundamental scale of gravity is higher than theorized. However, these results don't definitively rule out microscopic black holes. They simply push the energy threshold higher, potentially requiring future collider experiments with even greater energies to test these theories conclusively. Safety considerations and public concerns. The prospect of creating black holes on Earth sparked widespread public concern, forcing scientists to address some pretty fundamental questions about experimental safety. Public fears about CERN creating dangerous black holes have persisted since the LHC's inception, and honestly, they've been amplified by popular culture and social media speculation. CERN has consistently addressed these concerns through comprehensive safety assessments and public education. According to CERN's official safety documentation, any microscopic black holes produced would be perfectly safe because they would evaporate almost instantaneously through Hawking radiation. The fundamental safety argument relies on cosmic ray interactions. High-energy particles from space constantly bombard Earth's atmosphere with energies far exceeding the LHC's capabilities, up to 10 to the 20th electron volts. If dangerous black holes could be produced at LHC energies, cosmic rays would have already created them throughout Earth's 4.5 billion-year history. Dr. John Ellis and other CERN physicists have emphasized that even hypothetically stable microscopic black holes would be harmless because they would interact so weakly with ordinary matter that they would pass through Earth without effect. The LHC Safety Assessment Group concluded that the experiments pose no conceivable danger, with multiple independent reviews confirming these findings. Hawking radiation and quantum effects. Stephen Hawking's groundbreaking theory predicts that microscopic black holes wouldn't grow and consume matter. Instead, they would explode in bursts of quantum radiation. Hawking radiation theory, developed by Stephen Hawking in the 1970s, fundamentally changed our understanding of black hole behavior. According to this theory, black holes aren't completely black but emit radiation through quantum effects at their event horizons. For microscopic black holes, this process would be extraordinarily rapid. Objects with masses comparable to elementary particles would evaporate in approximately 10 to the minus 27 seconds. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. This creates a natural safety mechanism. Any microscopic black holes produced at CERN would immediately decay into standard model particles before they could interact with surrounding matter. The evaporation process would produce a distinctive spray of particles including photons, electrons, muons and quarks, creating detectable signatures in CERN's instruments. Theoretical calculations suggest that the temperature of Hawking radiation from a microscopic black hole would be incredibly high, potentially reaching 10 to the 17th Kelvin. This extreme temperature would cause the black hole to radiate away its entire mass almost instantaneously, making it impossible for such objects to grow or pose any danger to their surroundings. Implications for extra dimensions. The search for microscopic black holes at CERN represents honestly humanity's first experimental probe into the possibility that our universe contains hidden spatial dimensions. The theoretical models predicting microscopic black hole production are, intimately connected to theories of extra dimensions. These models suggest that our familiar three-dimensional space might actually be embedded in a higher dimensional reality, with gravity able to propagate through these additional dimensions, while other forces remain confined to our observable space. The ADD model, which was developed by Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, proposes that gravity appears weak because it spreads out through large extra dimensions. Meanwhile, the Randall-Sundrum model suggests that we live on a three-dimensional brain within a five-dimensional space, with gravity concentrated near our brain by the geometry of space-time itself. CERN's experimental limits on black hole production provide, crucial constraints on these theories. The absence of black hole signatures at current energy scales suggests that if extra dimensions exist, they must be smaller or configured differently than some models predict. These results represent the first experimental tests of quantum gravity theories, providing invaluable data for theoretical physicists working to understand the fundamental structure of spacetime and the unification of quantum mechanics with general relativity. Advanced detection methods. CERN's scientists, have developed some truly revolutionary detection techniques to identify the fleeting signatures of microscopic black holes among millions of particle collisions. The search for these tiny black holes required developing really sophisticated analysis techniques to distinguish potential black hole signatures from ordinary particle physics processes. The CMS and ATLAS detectors use these multi-layered systems, silicon trackers, electromagnetic calorimeters, and muon chambers, to reconstruct particle trajectories and energies with, honestly, extraordinary precision. Scientists have also developed specialized algorithms to identify the high multiplicity particle jets that would result from black hole evaporation, looking for events with unusually large numbers of particles produced in spherically symmetric patterns. On top of that, machine learning techniques have been employed to analyze vast datasets, training neural networks to recognize potential black hole signatures among the billions of collision events recorded. The analysis focuses on invariant mass distributions, searching for resonances or anomalies that just can't be explained by standard model processes. Researchers use Monte Carlo simulations, which incorporate various black hole models, to predict expected signatures, then compare these predictions against real data using statistical methods. The detection challenge is immense. Potential black hole events would be extremely rare, requiring analysis of petabytes of collision data to identify possible candidates among overwhelming backgrounds of ordinary particle interactions. Future prospects and higher energies. As CERN prepares for even more powerful experiments, the search for microscopic black holes is, well, entering a new phase with unprecedented energy scales. The high-luminosity LHC upgrade, which is scheduled for completion in the late 2020s, will actually increase collision rates by a factor of 10, providing vastly more data for rare event searches. This enhanced capability could push the search for microscopic black holes to higher mass scales, potentially reaching the thresholds predicted by some extra-dimensional models. Looking ahead, future collider projects, including the proposed future circular collider, with energies up to 100 TeV, would provide even more sensitive probes of quantum gravity effects. The increased energy and luminosity would allow scientists to explore black hole production at mass scales up to 50 TeV or higher, definitively testing many theoretical predictions. Advanced detector technologies under development like improved calorimetry and faster data acquisition systems will enhance the sensitivity to black hole signatures. Theoretical work is also continuing to refine predictions, with new models suggesting alternative signatures that might be more easily detectable. Really, the combination of higher energies, improved detectors, and more sophisticated analysis techniques may finally provide the experimental breakthrough needed to either discover microscopic black holes or definitively rule out their production at collider energies. The broader impact on physics. Whether CERN finds microscopic black holes or not, the search itself is, honestly, revolutionizing our understanding of fundamental physics and the nature of reality. The quest for microscopic black holes at CERN represents more than just hunting for exotic objects. It's really testing the very foundations of our understanding of space-time, gravity, and quantum mechanics. The experimental limits already established have constrained theories of extra dimensions and quantum gravity, forcing theorists to refine their models and develop new approaches to unifying fundamental forces. The sophisticated detection methods developed for black hole searches have advanced experimental techniques across particle physics, improving our ability to discover other new phenomena. The safety analyses conducted for these experiments have also deepened our understanding of cosmic ray interactions and astrophysical processes. Even negative results provide valuable scientific information, ruling out certain theoretical possibilities and guiding future research directions. The interdisciplinary nature of this research has fostered collaboration between particle physicists, cosmologists, and theoretical physicists, leading to new insights about the universe's structure. As CERN continues pushing the boundaries of experimental physics, the search for microscopic black holes remains a powerful probe of reality's deepest mysteries, potentially revealing whether our universe truly contains hidden dimensions and whether quantum mechanics and gravity can be unified into a single theoretical framework. CERN's search for microscopic black holes represents humanity's boldest attempt to probe the fundamental nature of reality itself. While no black holes have been detected yet, the journey has revolutionized our understanding of physics and pushed the boundaries of what's experimentally possible. If you're fascinated by these cutting-edge discoveries and want to explore more mind-bending physics mysteries, hit that like button, share your thoughts in the comments, and subscribe to Sci and Y for more journeys into the universe's deepest secrets. Thanks for watching. Keep questioning reality.